On February 25th, 2026, something happened that genuinely should not be possible. A historic blizzard ended, and the number of simultaneous National Weather Service alerts across America went up, not down. Up 616 active warnings at the same time, more than during the blizzard peak itself. Hurricane winds in Alaska, 90 degrees in Southern California, 20 inches of snow, and 83-mile-per-hour gusts in Colorado, simultaneously 100 miles apart. A moisture anomaly so statistically extreme it shows up roughly once in 3.5 million observations. One pattern in every direction, all at once. And if you think these are 5 separate stories, you are wrong. Because this is one story with 5 faces. Stay with me if this has you pulled in. Hit subscribe because this pattern is still evolving and we are not done tracking it. Drop a comment telling me where you're watching from and whether any of this is hitting your region right now. And if you want to help the Skylab grow, share this one. You are the reason we can keep doing this. Now, let's get into it. 616. That number was sitting on a screen at the National Weather Service on February 25th, 2026. And it was still climbing. Not 616 warnings for one storm. Not one type of hazard stacked up from one system grinding its way across the country. 616 simultaneous active alerts. Hurricane-force winds, wildfire conditions, river floods, blizzard-class snow, and temperature extremes, all live at the same time, all across the United States. All on a single Wednesday morning, here is what makes that number genuinely strange. Just days before the eastern seaboard had been buried under one of the more dramatic blizzards in recent memory, alert counts had surged to around 550 as that system peaked, which was already a significant number. Then the blizzard ended. The snow stopped falling on Boston and New York. The emergency declarations got lifted, and the alert count did not drop. It went up from 550 to 552 as the blizzard wound down. And then, instead of falling back toward baseline, it kept climbing. 616 by the time we're talking about it now. That is not how this is supposed to work. When the storm that drove the alerts ends, the alerts end, the count falls, the atmosphere takes a breath. Except this time it didn't. And the reason why tells you everything about what is actually happening to the American atmosphere. Right now, this is not 5 separate weather stories happening to coincide on the same day. It is one story, one amplified atmospheric structure expressing itself in 5 radically different ways across 5 radically different regions. The blizzard didn't resolve, it transformed. The same pressure configuration that buried the East Coast redistributed its energy. And what you're seeing now is the result. A pattern that didn't calm down, it just changed faces. Let's paint the picture quickly because the scope of this matters. In the Gulf of Alaska, the National Weather Service was issuing hurricane force. Wind warnings were not metaphorical ones, but actual sustained winds above 64 knots over open water. Southern California was looking at forecast highs approaching 90 degrees Fahrenheit in the last week of February. Northern California's rivers were pushing toward flood stage, with the Eel River already breaching moderate flood levels. In Colorado, a single ridge running along the foothills was simultaneously recording 83-mile-per-hour gusts at a site called Dakota Hill. This produced near-record warmth of 71 degrees in Denver and dumped 10 to 20 inches of heavy, wet snow across the Park and Medicine Bow ranges, all within 100 miles of each other. The Central Plains and Rockies were under red flag fire warnings. The Northeast was still sitting under a cold dome left over from the blizzard, and was getting clipped by lake effect and short-wave snow systems. And up in space, but we'll get to that. How does a weather system produce 90-degree heat and 20 inches of snow at the same time? How does the alert count go up after the storm ends? And what does a ridge trough configuration actually have to do with any of this? The answer is a concept called the pressure gradient superstructure. And once you see it, you cannot unsee it. The physics here is not exotic or controversial. What we're watching is textbook Rossby wave behavior, the planetary scale atmospheric waves that organize the jet stream into ridges and troughs, into high-pressure domes and low-pressure channels. Rossby waves are always there. They are always shaping weather. What is not always there is this level of amplitude. This degree of contrast between the ridge and the trough, sustained across these many days, producing these many simultaneous extremes at this level of intensity, the mechanism is understood. The magnitude is the story, and the magnitude is what we need to talk about next, because the 100-degree temperature spread sitting across the continental United States right now is not just a dramatic statistic. It is the engine. It is the fuel. It is the reason 616 alerts are active simultaneously, and it is the reason the count keeps climbing instead of falling. What the atmosphere does with that much thermal contrast, what that stream does when it has that much energy to work with, is where this story gets genuinely unsettling. There is roughly 100 degrees Fahrenheit of temperature difference sitting across the continental United States right now. And that number is not a curiosity. It is a structural condition. It is the thing that makes everything else on that 616 alert board possible. And it is worth pausing here to understand why. Because most coverage of extreme weather treats heat and cold as separate stories, as opposing teams, as things that cancel each other out. They don't in the atmosphere. They amplify each other. Think of the atmosphere as something that desperately wants to equalize hot air on one side of the continent, cold air on the other, and in between, a pressure gradient that the physics of fluid dynamics will not allow to sit still. The pressure gradient force, stated simply, is the force that drives air from regions of high pressure toward regions of low pressure. The steeper that gradient, the more compressed the distance between extreme cold and extreme heat, the more violent the response. You can write it as a relation. The force equals negative the gradient of pressure. Tighter gradient, stronger force. Stronger winds, more lift, more energy available to the system. What that means in practical terms is this. The 83-mile-per-hour gust recorded at Dakota Hill in Colorado on February 25th was not produced by some rogue local wind event. It was produced by an exceptionally steep pressure gradient between a ridge of warm high-pressure air parked over the western United States and a deep trough of cold low-pressure air digging into the central and eastern portions of the continent. The tighter that boundary, the more compressed that gradient, the faster the air accelerates across it. Colorado just happened to be sitting directly at the inflection point, which is why Colorado got all three extremes at once. But we'll come back to that. The same gradient that generated those wind speeds is doing other things simultaneously over the Colorado Rockies. Air moving rapidly from west to east gets forced up the western slopes, cools, saturates, and drops enormous amounts of precipitation, which at altitude in late February means snow. But the same air that rises on the west side of the mountains descends on the east side, compressing adiabatically. That's compressional warming. That's why Denver was approaching 71 degrees, while the mountains, 40 miles west, were measuring snow in feet. Meanwhile, that same pressure configuration was extending its reach. The jet stream, channeled and accelerated by the thermal contrast between the ridge and the trough, was delivering a moisture plume into Northern California. It's a corridor of atmospheric water vapor that river basins along the Eel, Russian, Nevada, and Sacramento don't have the infrastructure to absorb all at once. At the same time, Southern California was sitting under the warm, subsiding air of the ridge itself, insulated from moisture, baking at temperatures that belong in May. In Alaska, the deepening low-pressure system in the Gulf, the one generating hurricane-force winds over open water, was being fed by the same extended Pacific jet that the ridge trough configuration was stretching and intensifying. The cyclone didn't appear in isolation. It appeared because the upper-level trough provided the divergence aloft needed to spin up a powerful surface low, which then had an enormous fetch of open ocean to work with. Every one of these events, the Colorado gusts, the California split, the Alaska marine storm, the Northeast cold dome, the plains fire danger, traces back to one root condition: an amplified planetary wave sitting over North America, with a temperature contrast large enough to generate jet stream winds and pressure gradients of unusual intensity across thousands of miles simultaneously. Here is the part that should make you want to keep watching. That temperature contrast, that 100-degree spread, doesn't just produce the extremes we've already talked about. It produces anomalies at the statistical edge of what our models even account for. One of those anomalies showed up in a single column of air over Colorado, and it measured 5 standard deviations above normal. If you know what that means statistically, you already know why that number matters. If you don't, give me 90 seconds in Act 2, because it reframes everything. But first, Colorado. 100 miles. Colorado 1. 3 simultaneous extremes that by every reasonable expectation should not coexist. Let's go there. If you want to understand what a single amplified pressure gradient can actually do to a landscape of human infrastructure and lived experience, you don't need to look at the whole country. You just need to look at a 100-mile strip running from the Colorado foothills into the Park and Medicine Bowl ranges on February 25, 2026. At Dakota Hill, located in the foothills west of Denver, instruments recorded a gust of 83 miles per hour. To be clear about the magnitude of that number, that is hurricane equivalent wind speed at a land location in February. Those winds, driven by the steep gradient between the ridge, induced high pressure to the west, and the trough reinforced low pressure. Digging east, we're accelerating air down the eastern slope of the Rockies in what meteorologists call a downslope windstorm. This is a process where air descending the lee side of a mountain range compresses and accelerates, sometimes dramatically. The Front Range of Colorado is particularly prone to this under the right synoptic setup, and February 25, 2026 gave it about as favorable a setup as it gets. Those same winds, combined with the warm, dry air being advected eastward of the mountains, pushed relative humidity into single digits. Across the foothills and plains immediately east of the Front Range, red flag conditions were triggered across a wide swath of the region. This is the threshold at which fire can spread rapidly and unpredictably. This is not a theoretical fire risk. This is the kind of conditions that have ignited some of Colorado's most destructive fires in the last decade. Fires that have burned through communities in hours. The gradient that was producing record warmth at Denver International Airport was simultaneously turning the foothills into a tinderbox, and Denver itself, 40 miles east of the mountains, sitting on the high plains at 5,280 feet, recorded a temperature approaching 71 degrees Fahrenheit on February 25th. That is a near record high for the date. That warmth is not mysterious. It's the product of air. Descending from the mountain crest, it compressed at a rate of about 5.5 degrees per 1,000 feet, arriving on the plains 20 to 30 degrees warmer than it started. Denver's weather station measured the thermal signature of adiabatic descent almost perfectly on this day. Now go 40 miles in the other direction, west into the mountains, into the Park Range and Medicine Bow. At the same moment Denver was approaching 71 degrees, the mountains were measuring snow accumulation in feet. The National Weather Service Denver issued forecasts of 10 to 20 inches of accumulation across the higher elevations, with some areas potentially exceeding that under the most favorable orographic enhancement zones. These are ranges that can absorb significant snowfall, but the character of this snow matters. When air is warm and saturated, when the moisture content of the atmosphere is as anomalously high as it was on this day, snow ratios drop below 10 to 1. That means for every inch of snow water equivalent, you get less than 10 inches of snow. The result is heavy, wet, dense snow, the kind that snaps tree branches under its own weight, collapses roofs, and triggers wet slab avalanche conditions on steep terrain. Colorado's Avalanche Information Center was watching this closely for good reason. All three conditions, the 83-mile-per-hour gusts, the red flag fire danger, the heavy mountain snow, were being produced by a single short-waved trough moving through the amplified pattern, not three separate systems. One gradient, one structure, three simultaneous emergencies in 100 miles. The reason this matters beyond Colorado is that it illustrates something fundamental about how this pattern is operating nationally. The same dynamic that split Colorado into three simultaneous hazard zones is playing out at a continental scale. The ridge and the trough are not being polite enough to keep their hazards geographically separated. They are stacking them, concentrating them, generating conditions at locations that sit directly at gradient boundaries. And those boundaries, right now, happen to cut through populated regions with complex terrain and aging infrastructure. The National Weather Service office in Denver explicitly flagged something in its meteorological discussions that stopped people in the forecasting community. A precipitable water anomaly, measuring approximately 5 standard deviations above normal. 5 sigma. That phrase means something very specific in statistics and understanding. It is going to reframe everything we've covered so far, including why 616 alerts is a number you should not be comfortable with. Let's go deeper. Precipitable water is a measurement of how much water vapor is present in a vertical column of atmosphere from the surface all the way up to the top. If you could condense all of that vapor at once and let it fall as rain, precipitable water tells you how many inches of rain you'd get. It's a direct measure of how much moisture the atmosphere is carrying at a given location. On February 25, 2026, the precipitable water value over portions of Colorado was approximately 5 standard deviations above the climatological normal. The National Weather Service called it out explicitly in their technical discussions, which means it was anomalous enough that operational forecasters felt obligated to flag it for their colleagues. Here's what 5 standard deviations means in statistical terms. If atmospheric data were perfectly normally distributed, a bell curve, the probability of a value falling 5 standard deviations or more from the mean is roughly 1 in 3.5 million. You'd expect to see it by chance once every 3.5 million observations. Now, atmospheric data are not perfectly normal. Tail events occur more frequently in geophysical systems than a simple Gaussian model would predict. But even accounting for that, when NWS flags a 5 sigma signal, they are not doing so casually. They are telling you that the moisture loading in this column of air is genuinely exceptional. Not just unusual for the season, not just above average, but statistically extreme. The Z-score calculation is straightforward. Subtract the climatological mean from the observed value, divide by the standard deviation. A result of approximately 5 means the observation sits 5 standard deviation units above what is typical. Even with fat-tailed atmospheric distributions, a Z-score of 5 represents a signal that is hard to explain by random variation alone. So where did that moisture come from? The answer connects directly back to the central structure driving all of this: an atmospheric river. A narrow corridor of concentrated water vapor transport from the tropics and subtropics was being channeled inland off the Pacific and aimed directly at California and the broader Southwest. As that moisture plume encountered the topography of the Sierra Nevada and the Rockies, and as the dynamic lifting associated with the trough's passage maximized vertical motion at exactly the right location, the moisture was squeezed out of the atmosphere in extraordinary quantities. The alignment of moisture transport, topographic forcing, and dynamic lift was nearly optimal, which is exactly the kind of convergence you'd expect from an amplified ridge-trough configuration with a steep pressure gradient providing the mechanical forcing. Whether atmospheric river interactions with the Rockies are intensifying over time is a question researchers are actively working on. The data are suggestive in some studies, but this is not a settled question. And one event proves nothing. What we can say about February 25th is that the moisture anomaly was not random. It was generated by the same amplified wave pattern producing every other extreme on the board. The 5 sigma signal was not an independent curiosity. It was a symptom of the same engine we've been tracking since the first alert number appeared on that screen. And that engine was doing something remarkably similar thousands of miles northwest in one of the most hostile marine environments on Earth, while Colorado was trying to manage 3 simultaneous emergencies. Within 100 miles of each other, the Gulf of Alaska was experiencing something that would dominate headlines anywhere else on the planet. 6 separate hurricane-force wind warnings issued simultaneously across the marine zones with sustained winds of 55 to 65 knots and seas running 17 to 20 feet or higher. Those are not tropical hurricane conditions. Hurricane-force wind warnings in the marine context are issued when sustained surface winds meet or exceed 64 knots over ocean water. This is the same wind speed threshold that defines a tropical hurricane by the Saffir-Simpson scale, but without the warm core structure, the spiral bands, or the tropical origin. What the Gulf of Alaska storm had instead was an extratropical cyclone that had undergone rapid deepening under the influence of the upper-level trough extending from the same Rossby wave arc, affecting the lower 48. The divergence aloft associated with the trough provided the atmospheric evacuation that allowed surface pressure to drop quickly, spinning up a powerful surface low over a body of water with enormous fetch, meaning the wind had a very long, uninterrupted run across open ocean to build waves. 17 to 20-foot seas are what you get when you combine hurricane-force winds with that kind of fetch over an already rough water environment. The severity rating on these warnings was extreme, with immediate action required. This was the highest tier available. Accompanying those warnings were 84 heavy freezing spray warnings, which was the single largest count of any warning category. In the entire national inventory that day, freezing spray at a rate of 2 centimeters per hour or more accumulates on vessel surfaces rapidly enough to alter a ship's buoyancy and stability. It is one of the leading causes of vessel loss in high-latitude marine environments. 84 simultaneous warnings of that type represent an extraordinary marine threat across the Gulf geographically. There was also a magnitude 6.1 earthquake recorded near Nikolsky, Alaska, around this same period. Not causally related to the storm, but notable as a reminder that the region the storm was affecting is simultaneously one of the most seismically active and meteorologically hostile environments in the Northern Hemisphere. The Gulf of Alaska storm gets a fraction of the attention that a comparable event in the Gulf of Mexico or Atlantic would receive, partly because of its remoteness and partly because its impacts fall primarily on commercial fishing vessels and cargo ships rather than on densely populated coastlines. But the atmospheric significance of that storm is not remote at all. It was the Pacific expression of the same hemispheric Rossby wave arc that was simultaneously producing fire danger in Colorado, flooding in California, and anomalous warmth across the Southwest. The ridge-trough pattern doesn't have borders. It doesn't respect coastlines. It stretched from the Gulf of Alaska all the way to the northeast. The residual cold dome and every extreme we've discussed lived inside that same wave structure. This brings us to the state that was being cut cleanly in half by the boundary between the ridge and the trough on February 25th. It was a state that was simultaneously flooding in the north and approaching record heat in the south. California, as usual, had the most dramatic expression of the pattern's internal contradiction. California gets split by weather patterns with some regularity. The state is long, geographically complex, and climatologically diverse enough that Northern and Southern California can experience genuinely different weather simultaneously on a normal week. But what was happening on February 25th, 2026 was not a normal split. It was a demonstration of the same ridge-trough boundary that was already bifurcating Colorado and separating the marine environment of Alaska from the conditions in the lower 48. In Northern California, the rivers were running hard. The Eel River was already at moderate flood stage, with water levels threatening infrastructure and prompting emergency managers to issue evacuation advisories in portions of Humboldt County. The Russian, Navarro, and Sacramento rivers were at or approaching minor flood stage, with upstream gauge readings suggesting conditions would continue to rise through the afternoon and overnight hours. The moisture plume feeding these river systems was the atmospheric river we talked about. Considering Colorado's unusual precipitable water levels, the very same atmospheric river, carrying water vapor 5 standard deviations above normal over the Rockies, initially made landfall in Northern California. There, it unleashed enormous amounts of rain and snow onto terrain that rapidly channels water into the river basins. At their core, atmospheric rivers are relatively narrow, yet incredibly long corridors, often hundreds of miles wide and stretching thousands of miles, that efficiently transport vast amounts of water vapor from the tropics towards the poles. Their flow rates can even rival or surpass the average discharge of the Amazon River. Upon colliding with the coastal mountains and the Sierra Nevada, these rivers are forced upwards, rapidly shedding their moisture. While Northern California is generally well equipped to handle atmospheric river events, the sheer intensity of this particular one, exacerbated by the extraordinary moisture documented in the precipitable water data, overwhelmed the region's drainage infrastructure. Continue driving south, not even a great distance, relatively speaking. As you traverse the Sacramento Valley, enter the Central Valley foothills, and proceed past the transverse ranges, you'll find yourself in an entirely different atmospheric environment. On February 25th, Southern California was enveloped by the warm, dry, subsiding air characteristic of a high-pressure ridge. This phenomenon involves the slow descent of air from the upper atmosphere towards the surface, which adiabatically compresses and warms the air, effectively preventing cloud formation. Consequently, the region experienced clear, cloudless skies, remarkably low humidity, and temperatures soaring into the mid to upper 80s across the Los Angeles basin, with some inland valleys even nearing 90 degrees Fahrenheit. During the final week of February, temperatures ranging from 88 to 90 degrees in Southern California were a stark anomaly, more than 20 degrees above the climatological average for that time of year. This isn't just a warm day by any stretch. However, a 20-degree deviation above normal, occurring within a compressed late winter atmosphere over a region already grappling with year-round fire season, elevates this to an entirely different level of concern. The stark contrast between the moisture-laden, flood-stricken north and the hot, dry, subsiding south was so pronounced that, theoretically, one could drive through this transition zone in just a couple of hours, moving from a flood emergency directly into a heat advisory, without even pausing for fuel. This extreme sharpness of the boundary itself signifies the pattern's amplitude. During a more typical winter, California's weather systems tend to blend and transition smoothly. However, when an amplified high-pressure ridge presses firmly against a well-defined trough, their boundary becomes severely compressed. This creates a narrow, intense zone where atmospheric conditions shift dramatically over short distances and where extreme hazards on both sides manifest simultaneously. Is the persistence of high-pressure ridges intensifying over the western United States? Certain research suggests a link between Arctic amplification, the accelerated warming of Earth's polar regions, and an increased tendency for these high-pressure systems to become more stationary. Across the West Pacific and Western North America, the prevailing hypothesis posits that as the Arctic warms at a faster rate than the tropics, the crucial temperature gradient powering the jet stream diminishes. In response, the jet stream develops more expansive, slower-moving meanders, which in turn correspond to higher amplitude Rossby waves. These higher amplitude waves, in turn, lead to more persistent high-pressure ridges and low-pressure troughs, which remain stationary for extended periods, thereby intensifying their impacts on the underlying regions. However, this hypothesis remains a subject of debate. It is far from settled science. Indeed, some atmospheric scientists compellingly argue that such patterns can arise purely from natural variability, especially through interactions between the El Niño Southern Oscillation and the Pacific Decadal Oscillation, without necessitating any fundamental shift in the background climate state. Both perspectives are supported by peer-reviewed research, yet neither has definitively prevailed in the ongoing scientific discourse. What we can state with certainty is that on February 25, 2026, the high-pressure ridge was present, the low-pressure trough was present, and their dividing line effectively bisected California. Simultaneously, this very same pattern was influencing the entire alert board, encompassing all 616 items, even those 93 million miles distant. However, an additional layer to this narrative emerged, presenting either a remarkable coincidence or a scientific enigma yet to be fully unraveled. On February 25, 2026, the solar disk appeared almost entirely spotless, with active regions being remarkably minimal. The probability of a solar flare, specifically a significant X-ray burst from a solar eruption, registered at 0% according to standard solar activity measurements. By all indications, this should have been a tranquil day for space weather. Nevertheless, the solar wind was observed traveling at approximately 549 kilometers per second, and the KP index, a global metric for geomagnetic disturbance, had climbed to KP4. This level marks the lower threshold of active geomagnetic conditions. Furthermore, electron flux at geosynchronous orbit was recorded at 13,748 particle flux units, a sufficiently elevated reading to warrant logging and monitoring by satellite operators. The perplexing question then arises: how can active geomagnetic conditions manifest from an otherwise spotless sun? The explanation lies in corona holes. A corona hole is a specific region within the sun's outermost atmosphere, the corona, where the magnetic field lines extend outwards into space instead of curving back towards the solar surface. It is through these open field lines that the solar wind streams forth at an accelerated velocity. This process propels a continuous stream of charged particles outwards, which, if directed towards Earth, can interact significantly with our planet's magnetosphere. Such interactions are capable of generating geomagnetic activity even without the occurrence of solar flares or coronal mass ejections. In contrast, space weather driven by flares typically manifests as sudden and dramatic events. It's a brief, intense burst, often followed by a coronal mass ejection, which, if it impacts Earth, can trigger a rapid onset of storms. This can lead to significant geomagnetic disturbances within a matter of hours or days. Coronal hole-driven space weather, however, operates differently. It's slower, more sustained, and typically recurs on roughly the same 27-day rotation cycle as the Sun itself. If a coronal hole is currently facing Earth, it will approximately face Earth once more in about 27 days, assuming the hole hasn't significantly evolved or dissipated. In the meantime, there's no confirmed mechanism linking coronal hole-driven solar wind streams to jet stream behavior or tropospheric weather patterns. When such a connection is proposed, it remains a subject of active research and contested claims. The honest assessment here is that over 3 consecutive days, centered on February 25th, geomagnetic activity produced by an elevated solar wind stream from a coronal hole coincided with an exceptionally amplified atmospheric pattern, driving 616 simultaneous weather alerts. Is that causation? No evidence supports that conclusion. Is it coincidence? Almost certainly. Is it a question worth flagging, especially since this channel exists? Precisely to highlight questions that mainstream coverage often overlooks? Yes, it is. What we can say with confidence is that both the atmospheric pattern and the geomagnetic activity share a key structural characteristic. They both represent an elevated, sustained energy input. Rather than a brief spike followed by a return to baseline, the solar wind stream wasn't a mere one-hour event. It was a multi-day flow from a persistent coronal hole structure. Similarly, the atmospheric pattern wasn't a one-day event either. It began before the blizzard, persisted through the blizzard, reconstituted itself after the blizzard, and by February 25th, it was producing more simultaneous alerts than the blizzard's peak itself had generated. This demonstrates persistence in 2 separate systems. Operating on 2 distinct scales, and approximately 27 days from now, give or take the evolution of that coronal hole, the solar component of this entire picture may be worth re-examining. The Sun rotates approximately once every 27 days, as observed from Earth. Technically, its sidereal rotation period is about 25 days. But since Earth is also moving in its orbit, the apparent rotation from our perspective is closer to 27 days. Coronal holes, naturally, rotate with the Sun. If a coronal hole is optimally positioned to direct its solar wind stream toward Earth today, the straightforward frequency calculation of 1 cycle per 27 days suggests a potential recurrence window around late March. However, this isn't a prediction. Coronal holes evolve. They can shrink, expand, or dissipate over a rotation period. Solar cycle Jupiter, currently in its declining phase, is generally expected to feature coronal holes, becoming somewhat more prominent as activity in active regions diminishes. This aligns with our current observations of a spotless or near-spotless solar disk. Whether the specific coronal hole responsible for the February 25th elevated solar wind will persist and maintain its Earth-directed geometry through another rotation is genuinely unknown at this point. Nevertheless, it represents a monitoring window worth noting, and it reinforces the broader theme here. These are not patterns that merely spike and vanish. They are patterns that persist, recur, and compound. The same persistence that makes a recurring coronal hole relevant is precisely what makes the atmospheric pattern we've been tracking so consequential. This brings us to the central question this entire story has been building toward. What exactly are we seeing on February 25th, 2026? Is it merely a natural fluctuation within normal atmospheric variability, or is it evidence of something fundamentally shifting in how the atmosphere operates? That question deserves more than a dismissive answer in either direction. Consider this: 616 simultaneous alerts, and the alert count actually increased after the storm that was supposedly driving it had ended. Let's pause and consider that for a moment, because it's precisely this detail that should be generating the most serious discussion in atmospheric science right now. And it's often this very detail that gets lost when media coverage focuses on individual extremes rather than the complex system producing them. A compound extreme event is broadly defined as the coincidence or rapid succession of multiple extreme weather or climate events that result in impacts more severe than those of any single event alone. This concept has gained significant traction in research over the last decade, precisely because infrastructure, emergency management, and adaptation planning are typically designed for single hazard scenarios. For instance, a power grid designed to handle a major ice storm can be overwhelmed if that ice storm occurs on top of a wind event that has already strained the system. A flood control system designed for a major atmospheric river can fail if the watershed is already saturated from a preceding precipitation event. Similarly, emergency resources deployed for a blizzard response cannot simultaneously manage wildfire evacuations, marine search and rescue operations, and flood emergency coordination. The 616 alerts on February 25th were not 616 versions of the same problem. They were distributed across categories like hurricane-force marine wind, coastal flood, river flood, blizzard, and winter storm. They also spanned high wind, red flag, fire, and extreme heat categories. This multi-category distribution meant that the national emergency response architecture was being asked to address genuinely different kinds of emergencies simultaneously in different regions, each with distinct resource requirements. You cannot pull fire suppression aircraft to assist with flood rescue, nor can you redirect Marine Coast Guard assets to help with mountain avalanche rescue. Now, a legitimate caveat is necessary here. The National Weather Service has expanded and refined its alert categories significantly over the decades. Some portion of any increase in alert counts over time reflects improvements in detection, modeling, and the institutionalization of new warning types. This is rather than purely a change in atmospheric conditions. Alert: inflation is real, and anyone who ignores it is not being straight with you. We should be honest about it. But the multi-category spread of February 25th alerts is harder to dismiss as a product of category inflation. The events themselves. The 83-mile-per-hour gusts at Dakota Hill, the Eel River flood stage breach, the hurricane-force marine warnings in Alaska, the Northern California atmospheric river, the near-record heat in Southern California are real, measurable, instrument-verified phenomena. And their simultaneity, this is tied to a single pressure gradient superstructure, which is what makes February 25th a legitimate case study for compound extreme research. What the research asks, and has not yet definitively answered, is whether events like February 25th are increasing in frequency, in intensity, or in geographic scope. This is made more complex by the fact that what matters may not be the average condition, the mean, but the variance. A world in which the average February temperature is 1 degree warmer may be less consequential for infrastructure than a world in which the amplitude of temperature swings from week to week has increased. Even if the mean hasn't shifted dramatically, sharper contrasts, not just warmer averages, may be the more consequential signal to watch. Since the blizzard days ago, this pattern hasn't relaxed. It has restructured. It has maintained its amplitude, rotated its hazard zones, and produced more total alerts at the post-blizzard stage than it did at the blizzard peak. That is persistence. And persistence, in the context of compound extremes, is what converts individual events into sustained infrastructure stress. The jet stream is the governor of all of this, and whether the jet stream is changing or whether we are simply experiencing the natural range of its variability is one of the most contested and consequential debates in atmospheric science right now. The jet stream is a narrow band of fast-moving air in the upper troposphere, driven by the temperature contrast between the tropical and polar regions of the planet. It flows generally from west to east at altitudes between 25,000 and 45,000 feet, and it is the organizing structure that determines where storm tracks develop, where cold air masses push south, where warm air is advected north, and how long any given weather pattern persists before being swept downstream by the flow under normal conditions. The jet stream maintains a roughly zonal flow, moving primarily east-west with modest northward and southward undulations. Rossby waves are always present in the jet, but their amplitude and phase speed determine how extreme and how persistent any given weather pattern becomes. Large amplitude waves develop deep ridges and troughs. Slow-moving waves allow those ridges and troughs to sit over the same regions for extended periods. Persistent ridges and troughs mean persistent weather. Prolonged drought under a persistent ridge, extended cold snaps under a persistent trough, repeated flooding from systems that keep arriving in the same corridor. The scientific debate about the jet stream centers on a hypothesis that has gained significant attention over the last 15 years, associated with researchers including Jennifer Francis and Stephen Vavras, among others. The core argument is this: as the Arctic warms faster than the rest of the planet, a phenomenon called Arctic amplification, which is observationally well documented, the temperature gradient between the tropics and the Arctic weakens. Because jet stream speed is tied to that gradient through thermal wind balance, a weakened gradient produces a slower, more meandering jet. A slower, more meandering jet develops larger amplitude. Raptor waves' larger amplitude waves move more slowly, persist longer, and produce more intense impacts beneath them. This hypothesis, if correct, would provide a mechanistic link between long-term global temperature change and the kind of amplified, persistent, multi-hazard atmospheric pattern we observed on February 25, 2026. It would suggest that events like this, not just warming, not just individual extremes, but the simultaneous stacking of contradictory extremes driven by high-amplitude, slow-moving wave patterns, might become more common as background conditions continue to evolve. But the hypothesis is contested, and that contestation is legitimate. Some research groups argue that the observational evidence for jet stream winding is inconsistent across datasets and time periods. Others argue that natural variability, particularly the phasing of El Niño, Southern Oscillation, and the Pacific Decadal Oscillation, which are known to influence ridge and trough position over North America, can produce patterns indistinguishable from what the Arctic amplification hypothesis would predict, without requiring any change in the climate background state. A deep La Niña or a positive Pacific Decadal Oscillation phase can anchor a persistent ridge over the western United States and a persistent trough over the eastern United States for weeks at a time, producing exactly the kind of split we've been describing. What makes the scientific debate genuinely difficult is the signal-to-noise problem. The climate system is noisy. Natural variability is large. Detecting a trend in wave amplitude or jet stream speed is statistically distinguishable from natural fluctuations. Requires either very long data records or very clear signals. And the literature currently has significant disagreement về việc liệu tín hiệu của sự khuếch đại Bắc Cực lên dòng tia đã có thể phát hiện được hay chưa, vượt lên trên mọi nhiễu loạn. Điều không thể tranh cãi là mô hình thời tiết chúng ta quan sát được vào ngày 25 tháng 2 đã không tan biến sau trận bão tuyết. Nó vẫn tiếp diễn, phát triển và tái cấu trúc sự phân bố các mối nguy hiểm mà không mất đi biên độ cơ bản của mình. Sóng áp cao vẫn ở nguyên vị trí, rãnh áp thấp cũng vậy. Độ chênh lệch giữa chúng, vốn là động lực của mọi điều chúng ta đã mô tả, vẫn đủ lớn để duy trì 616 cảnh báo đồng thời đang hoạt động và tiếp tục tăng. Liệu sự kéo dài đó là dấu hiệu của một điều gì đó mới trong hệ thống khí hậu hay chỉ là một biểu hiện đặc biệt dữ dội của biến đổi tự nhiên? Câu hỏi đó vẫn chưa có lời giải đáp rõ ràng. Nhưng đó chính là câu hỏi mà ngày 25 tháng 2 năm 2026 đang buộc cộng đồng khoa học phải nhìn nhận một cách nghiêm túc. Có một điểm khác biệt hiếm khi được đề cập trong các bản tin thời tiết, nhưng có lẽ là khái niệm quan trọng nhất để hiểu một mô hình như ngày 25 tháng 2 thực sự nói lên điều gì về hướng đi của hệ thống khí hậu. Khi chúng ta nói về biến đổi khí hậu trên các phương tiện truyền thông phổ biến, chúng ta thường đề cập đến giá trị trung bình. Nhiệt độ trung bình đang tăng, mực nước biển trung bình đang dâng và các mô hình lượng mưa trung bình đang dịch chuyển. Những thay đổi về giá trị trung bình này là có thật, đã được ghi nhận và mang lại những hậu quả nghiêm trọng. Nhưng có một khía cạnh thống kê thứ hai có thể quan trọng hơn đối với cơ sở hạ tầng, quản lý khẩn cấp và trải nghiệm sống hàng ngày trong bầu khí quyển. Đó là phương sai. Sự thay đổi phương sai có nghĩa là sự phân bố các kết quả đang mở rộng, rằng các hiện tượng cực đoan ở cả hai đầu đang trở nên khắc nghiệt hơn, ngay cả khi giá trị trung bình không thay đổi đáng kể. Trong một thế giới với phương sai khí quyển tăng lên, bạn không chỉ có nhiệt độ trung bình ấm hơn, bạn còn chứng kiến những dao động lớn hơn. Bạn sẽ trải qua những đợt lạnh sâu hơn cùng với những đợt nắng nóng dữ dội hơn. Bạn sẽ gặp những trận mưa lớn hơn cùng với những đợt hạn hán kéo dài hơn. Bạn sẽ thấy sự chênh lệch nhiệt độ lớn hơn trên những khoảng cách ngắn hơn. Nói cách khác, bạn sẽ có các cấu hình sống áp cao và rãnh áp thấp được khuếch đại, tạo ra sự chênh lệch nhiệt độ hàng trăm độ trên lục địa và 616 cảnh báo đồng thời. Hệ thống khí hậu là phi tuyến tính, những thay đổi nhỏ trong điều kiện nền có thể tạo ra những thay đổi lớn không cân xứng về tần suất và cường độ của các sự kiện cực đoan. Điều này không có nghĩa là bầu khí quyển đang trở nên tận thế. Nó đang nói rằng nếu phương sai của hệ thống đang tăng lên, nếu các dao động quanh giá trị trung bình đang có biên độ lớn hơn, thì cơ sở hạ tầng được thiết kế để xử lý phạm vi điều kiện khí quyển trong lịch sử đang bị thách thức. Sự biến đổi có thể bị đánh giá thấp một cách có hệ thống so với phạm vi mới. Ngày 25 tháng 2 năm 2026 có thể trong tầm nhìn dài hạn là một điểm dữ liệu trong xu hướng tới các biến thể cao hơn, hoặc nó có thể là một sự kiện ngoại lai trong một hệ thống chưa thay đổi cơ bản. Cả hai khả năng đều phù hợp với tình trạng khoa học hiện tại. Điều không mơ hồ là mô hình 6016 cảnh báo đó không giống như nhiễu nền thông thường. Nó trông giống như một tín hiệu. Liệu tín hiệu đó có cho chúng ta biết điều gì đó bền vững về hành vi tương lai của bầu khí quyển hay không là câu hỏi mà dữ liệu từ những ngày như thế này cuối cùng sẽ giúp trả lời. Mô hình này vẫn đang tiếp diễn. Điều này đưa chúng ta trở lại điểm khởi đầu. 616 cảnh báo đang hoạt động, đồng thời và đang tăng lên sau khi trận bão tuyết lẽ ra đã kết thúc câu chuyện. Hãy quay lại con số đó một lần nữa, bởi vì nó không chỉ là một số lượng, nó là một mô tả về trạng thái của một hệ thống, một thống kê về số lượng địa điểm trên khắp Hoa Kỳ, đồng thời ở trong điều kiện đủ nguy hiểm để yêu cầu chính thức. Cảnh báo công khai vào ngày 25 tháng 2 năm 2026. Gió bão trên vịnh Alaska với sóng biển cao gần 6 mét, nhiệt độ gần kỷ lục lên tới 32 độ C khắp Nam California vào tuần cuối tháng 2. Các con sông ở Bắc California đang tiến đến mức lũ, được cung cấp bởi một luồng hơi ẩm bất thường, đến mức Dịch vụ Thời tiết Quốc gia cảm thấy buộc phải đánh dấu nó bằng ngôn ngữ của các hiện tượng cực đoan thống kê. Gió giật 133 km/h, nguy cơ cháy rừng cao và 50 cm tuyết trong vòng 160 km ở Colorado. Một khối khí lạnh bao trùm vùng Đông Bắc vẫn tạo ra tuyết từ các hệ thống bão nhỏ và hiệu ứng hồ. Một bóng ma dai dẳng của trận bão tuyết lẽ ra đã tan biến. Và trong không gian, một lỗ vàng nhật hoa đang phun gió mặt trời qua trái đất với tốc độ 549 km/giây, đẩy môi trường điện tử hướng tới hoạt động tăng cường. Dưới một mặt trời mà theo mọi tiêu chuẩn trông như không làm gì cả, mọi mục trong danh sách đó, mọi cảnh báo, mọi hiện tượng cực đoan khu vực đều được kết nối với một cấu trúc siêu áp suất gradient được khuếch đại duy nhất, một sống áp cao, một rãnh áp thấp, một sự tương phản nhiệt độ lớn trải dài từ khối khí Bắc Cực trên Trung và Đông Lục Địa đến khối khí ẩm ấm trên nội địa phía Tây. Cơ chế không hề bí ẩn, sóng Rossby, cân bằng gió nhiệt, lực gradient áp suất. Đây không phải là những ý tưởng xa vời, chúng là vật lý nền tảng của động lực học khí quyển, là những phương trình mà các dịch vụ thời tiết trên khắp thế giới sử dụng hàng ngày để tạo ra dự báo. Điều không bình thường là cường độ, điều không bình thường là sự kéo dài. Mô hình này không kết thúc khi trận bão tuyết tan, nó không biến mất khi tuyết ngừng rơi ở bờ đông. Nó đã tái cấu hình, phân phối lại năng lượng, thay đổi bộ mặt mà nó thể hiện từ một trận bão tuyết sang một mô hình đa nguy hiểm đồng thời, khiến số lượng cảnh báo tăng cao hơn chứ không giảm ly trong những ngày sau đó. Sự tiến hóa đó là chi tiết khiến bất kỳ ai chú ý đều phải cảm thấy không thoải mái với những câu trả lời dễ dàng. Nhìn về phía trước, từ ngày 25 tháng 2, các mô hình dự báo ngày 6 và ngày 7 đã cho thấy sự chia rẽ trong sự đồng thuận của tập hợp về cơn bão mùa đông tiếp theo đang phát triển ở miền Tây Hoa Kỳ. This meant forecasters were grappling with significant uncertainty regarding where the next major event would strike and its potential intensity. Southern California's near-record heat anomaly required verification. The forecast was so remarkable that operational meteorologists were closely monitoring it, trying to discern if the models were capturing a genuine phenomenon or simply running warm. The critical question was whether the overall alert count would normalize or continue its upward trend. The behavior of that number in the days after February 25th offered a direct indication of whether the pattern was sustaining its intensity or finally starting to subside. Furthermore, the coronal hole, appearing 27 days after a favorably positioned coronal hole stream in late March, would offer another opportunity to monitor for heightened solar wind and geomagnetic activity. On February 25th, none of these pressing questions had clear answers. This isn't a failing of meteorological science. Rather, it's precisely what a truly complex, significantly amplified, and unresolved atmospheric pattern manifests as in real time. What we do know is this: the underlying mechanism is understood, and the physics are not in dispute. The Rossby wave generated the gradient, which in turn created the winds, the fire conditions, the orographic snow, the atmospheric river, and the compressional warming. This also led to the subsidence heat and the marine cyclone structure, 616 simultaneous manifestations of the same phenomenon. What remains unknown is whether such patterns are becoming more frequent, more intense, or more enduring. Alternatively, will February 25, 2026, in hindsight, be seen merely as an exceptionally challenging day within a naturally variable system, rather than a clear harbinger of a system whose fundamental rules are subtly shifting? The data will accumulate, the models will be rigorously evaluated, and the research will persist. However, what truly troubles atmospheric scientists isn't the storms or the alerts themselves, but the unsettling possibility that the atmosphere is no longer merely fluctuating around a stable, fixed center. The concern is that the atmospheric center itself might be shifting, that its oscillations could be growing in magnitude, and that what we term extreme events might be occurring with increasing frequency, pushing into a range once reserved for generational outliers. With 616 alerts, the mechanism is understood, but the magnitude remains uncertain, and the pattern continues to unfold. And it is precisely within that chasm between what we can explain and what we are not yet able to predict that the most profound question the atmosphere has ever posed to humanity resides. We simply haven't deciphered the answer yet.